Namaste student. Today we are going to prove the irrationality of number of the form root 2, root 3, root 5, dot 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 root p, where p is prime number. So if you see one of them, then rest you can prove by your own. Okay, we'll see how to prove the root 2 is irrational number. So here, before starting, let recapitulate our two topic. One is this one, last theorem. Last theorem we have discussed this one. If p divide a square, then p divides a, where p is prime number and a is any positive integer. And one more is there. If p divides a, then a can be written as p into c for some integer c. For example, 3 divides 18. That means 18 can be written as 3 into 6. If we'll take 5 divides 35, then you can write 35 equals to 5 into 7. So here your c is 7. Okay, so let's start. So we're going to prove this, it is a theorem. So we're going to prove this theorem by contradiction method. So here the contradiction means first we'll assume this one as a rational and then we'll check the property of rationality. Okay, if we'll see that if it match, then we'll say that yes, it's okay, our supposition is right. But if do not match with rational property, then we contradict our assumption and we'll say that root 2 is a irrational number. So we'll use our contradiction method. First we'll suppose or we assume that your root 2 is an irrational number. So let us assume that root 2 be a rational number. So by definition of rational number, we can write root 2 as p by q, where p and q are co-primes. That means HCF of p and q equals to 1. That means we have taken a simplest form. Now what we're going to do, we'll square both the side. So if we're squaring both the side, you will get here 2 equals to p square by q square. You can write here this one 2 into q square equals to p square. So look at here. If we'll take like this one, 5 into 7 equals to 35, then you can write that 5 is a factor of 5 is a factor of 35. Similarly, 7 is a factor of 35. So here look at here, 2 is one integer and q square is also an integer. So two integers are here. So our demand is here 2. Look at here, we have here this one 2. So 2 is a factor of p square. Similarly, q square is also a factor of p square, but we will not choose this one. It's not our demand. Our demand is this one. So we'll take this one as, we can write here 2 is a factor of p square. That means 2 divide p square. Now look at here, p is any integer here, because by definition p and q are integer. So here 2 is your prime number. Look at the formula, not formula, theorem, that if p divides a square, then p divides a, and here p is a prime number and a is any number, and here p is your any number and 2 is prime number. That means we can write 2 divides p. That means p can be written as 2c for some integer c. So take this one as your take this one as your number 1, this one is your number 2. Now substitute the value of p in equation 1. If you substitute, so here substituting the value of p in equation 1, what we get? 2 into q square equals to 4c square. So this 2 cancel, it will give you 2. That means 2c square equals to q square. And look at this one, the way we have done here, 2 into q square equals to p square. So here also same thing we are getting, 2 into c square equals to q square. That means similarly next step we can write like that 2 divides q square. This implies 2 divides q, because q is also a integer and 2 is prime number. That means we are applying this theorem. So sorry, this one 2 divides q. Look at this one is your number 3. Here can you see one thing, in equation 2, 2 divides p. That means 2 is a factor of p. 2 divides q. That means 2 is a factor of q. So here 2 is common factor of p and q. So what we can see from which equation? From 2 and 3. From 2 and 3 we get, what do we get? 2 is a common factor of p and q. But by definition what we have written, but HCF a p and q equals to what? 1. Look at here, HCF of p and q equals to 1. How could it possible? We have already assumed that HCF of p and q equals to 1, but after solving we are getting here 2 is a common factor. That means it contradicts our assumption. This contradict our assumption. What assumption? We assume that, what we have assumed? Root 2 is a rational number. That means our assumption is totally wrong. Whatever assumption we have taken, that contradict at the end here. That means we can say that hence root 2 is an irrational number. Now see, if they will ask you, prove that root 3 is an irrational number. So how are you going to prove? Instead of using root 2, you write here root 3. Okay, and then out of this one you choose 3. Here replace 3. Okay, replace 2 in the place of 3. So you can see here 3 divides p. Similarly p equals to 3. See, wherever you see the value, this one will give you 9 and cancel 3. That means 3c, 3 and 3. Have you seen? And this one will contradict that 3 is a common factor of p and q. But again we can see that HCF of p and q equals to 1. This contradicts our assumption. So similarly here, if they will ask you for root of 5, in the place of root 3 you use root 5. Whatever value they choose, if they are prime, then you can follow this step and you can prove it. Okay, I hope you have got. Thank you. See the step here.